In the previous lecture, we've realized through a mathematical point of view why transonic aerodynamics needs to be addressed dedicatedly. Okay, so in the third third lecture, we will go through actually two important concepts in the transonic aerodynamics. One is the so-called critical Mach number, the other is the drag divergence Mach number. Okay, so first of all, let's see the critical Mach number. Now suppose an aerofoil as shown here, and it's a bit exaggerated, it looks like an elliptical, but let's say it's an aerofoil, and it's in a Mach 0.3 free stream, and we will find point A. At point A, we have the maximum Mach number. Now I give a question to you. If this location A has a maximum Mach number over the aerofoil surface, and how about its pressure? Yes, the pressure will be the minimum in this case. Okay, so now what happens is we will increase the Mach number slightly, and now the free stream Mach number is 0.5, and we can see the maximum Mach number at the aerofoil top surface. It still appears at A, and MA becomes 0.772. So there is a bit increase of the local maximum Mach number. Okay. Now, if we increase the free stream Mach number further to 0.61, and we can see at this point, the Mach number at point A becomes 1.0. So it's exactly the sonic speed. And you may realize that I highlighted the numbers in red. For this case, it must be something special. That's right. So in this case, the free stream Mach number is called the critical Mach number. Okay. So basically, critical Mach number is a free stream Mach number when a point over the aerofoil or the wing has reaches sonic speed. And if we increase the free stream Mach number further, so now let's say if it happens at 0.65, we will see there will be a bubble region containing the supersonic flow, and now point A is no longer the maximum, has a maximum Mach number, local Mach number over the aerofoil. So, and this is a sequence of the when we increase free stream Mach number, what will happen over the aerofoil. And apparently the most important one in this case is when Mach number at point A is sonic speed, 1.0. Okay, so now let's define the critical Mach number, MACR. So critical Mach number is a free stream Mach number at which sonic flow is first achieved on the aerofoil surface. So this is a definition. We need to remember this. And now I have a question. And do we desire a higher critical Mach number or a lower critical Mach number? I will give you a few seconds to reflect. Yes, we prefer a higher critical Mach number. Why? Because that would postpone the appearance of the sonic flow or supersonic flow over the aerofoil. And for example, if we look at this aerofoil again, so for this case, we have 0.61, the critical Mach number. If we can delay the critical Mach number to 0.7 something, then the supersonic flow will be delayed. The appearance of the supersonic flow will delay. Then the drag increase also will be delayed. And perhaps you already have heard the name supercritical aerofoil. So why it's called supercritical? Because the critical Mach number for that type of aerofoil is larger than a conventional one, perhaps like the one showing here. So we will visit the supercritical aerofoil later and describe its features. Now let's move to the drag divergence Mach number, and I've included a curve in here. So the horizontal axis is free stream Mach number, and the vertical axis is the drag coefficient. What it describes is drag coefficient increase or drag coefficient variation with respect to the increasing free stream Mach number. And I have indicated the critical Mach number at point C, and also the so-called drag divergence Mach number at point E. And also, there are multiple points A, B, C, D, E, F, G. And let's do some explanation, see what happens to this curve of CD versus MA infinity. Okay, so we will look at the different sections of this curve. Now, first of all, we see section A to C, which is a flat part, initial part of this curve until critical Mach number. So the feature for this AC section, ACD maintains a similar small magnitude, and there's a little variation about CD until critical Mach number, which means until the supersonic region to appear, bubble to appear. Then let's take a look at point D. Point D, at this point, there will be a finite region of supersonic flow appearing on the aerofoil, and the Mach number in the bubble, in the supersonic bubble, is slightly above 1. It's very weak supersonic flow, so it's 1.02 and 1.05. So you can see it's only slightly above 1. So that's at point D. And now if we move to point E, which is the drag divergence Mach number, so you can see why it's called divergence. Perhaps we've done computational fluid dynamics CFD analysis. And one important criteria is we need to consider or expect the convergence of the residue in CFD. But if divergence happens, means that the residue will blow up. It's the same for the drag coefficient. If the drag starts to increase, to blow up, we call it drag divergence. There's a divergence happening. That's why we call it drag divergence Mach number. Okay, you can see comparing the CD at C and E, and it's there's substantial increase, right? And then we move to section E, F, and G. So there is a big increase of CD by a factor of more than 10. And because the drags increase substantially, and we call this some barrier. So in order to fly at such a CD, you need to address or overcome the drag induced at this regime. And there will be an extensive region of supersonic flow over the aerofoil, as shown in here. So we will have a very large area of supersonic flow. For example, on the top surface, the supersonic region nearly covers more than 2/3 of the up surface and more than half of the lower surface. So in this case, there will be significant drag induced. And the Mach number in those bubbles, in those supersonic regions, will be stronger supersonic Mach number. It can be as high as 1.2 and might be even higher. And also shockwaves will appear on both sides of the airfoil, and it can cause flow separation. And we can see the flow separation indicated as here, and also there's strong wake. And however, we've introduced a drag divergence Mach number. There's no precise definition of it. That's true. And if we look at the literature, the reference books, such as the Anderson book, there's no precise definition of the drag divergence Mach number. It can be qualitative definition, I would say. People usually say when there's significant increase of drag, and so at the critical drag divergence Mach number, the drag coefficient starts to increase dramatically. And also different manufacturer has different criteria to judge when the drag divergence Mach number happens. Okay, so it might be determined as a factor of 5 or factor of 6, but we know what's roughly the drag divergence Mach number is, so it should be higher than critical Mach number. And then let me ask a question, another question. If is it possible the aircraft fly at any point between C and E? So is that economical, or in practice does the aircraft fly between C and E? The answer is yes. And for example, the video we've seen earlier, and we already see in practice on the wing, we can see the shock wave, which means there is supersonic flow, so the aircraft was cruising at a point between C and E. So in practice, the aircraft may cruise at a Mach number higher than a critical Mach number, but it must be flying lower than a drag divergence Mach number. So through these two slides, we should be familiar with the critical Mach number and the drag divergence Mach number. And okay, so if we move further, we haven't finished yet. If we move further to point G, and we can see beyond that, the CD start to decrease, and G is approximately at Mach infinity about 1.0. So once the flow free stream Mach number is going beyond 1, which means the supersonic incoming flow, the drag will decrease slightly. Okay, so now we get a bigger picture, full explaining of this curve. And although some of the flow features are not clearly presented in here, we just use a sketch, for example, to show you the point at the drag divergence Mach number. Okay, so in the next lecture, we will have a better or detailed view of the flow field at each section, and also you may already wonder what happens to CL, the lift. So we have we've seen the CD in here. What about CL? What happens to the CL in relation to CD? This will be the question for the next lecture. Thank you.